Hello, this is Ben Zimmer from Enable Training and Consulting, bringing you the next installment of the LV Mastery Tip Jar. In this installment, we're going to talk about the Dashboard project from the point of view of the FRC First Robotics competition. This is the project which will allow us to use a computer at our driver station which communicates with the robot in competition. Let's begin by opening up the robot project which we created over the last few tip jar videos. Recall that what we've previously done is to create a sub-VI which contains a state machine to control a mechanical lifting assembly. We've added a debugging dashboard which allows us to internally debug but will not work during competition. And we've also added a simulated mode within our lifter sub-VI. So let's proceed now by talking about this VI. This is the dashboard data VI. Let's open it up. On the block diagram of this VI, we see at its heart a while loop which runs forever until the program is manually terminated, and two shift registers, the top which is a numeric and the bottom which is a cluster. There's a little bit of documentation here which tells us that the top loop is actually a counter. The purpose of the counter is to keep track of how many times this loop has run. And the reason we want to do that is we want to perform different actions depending on what stage we are in running. It's described as saying to disperse work across 50 calls to keep overhead low. And the way that works is to use this function, which is the quotient and remainder VI. Essentially, it takes this number, divides by 50, and gives you out the remainder. So we know that the remainder will always be between 0 and 49. And so, using this case structure here, depending on the value of that remainder, different tasks will be performed based on the value of the counter. So we're going to modify this to contain our own custom information and to send that back to our dashboard application, which is going to be running back on the driver station computer. So we're going to need to make modifications to this case structure, and we're going to need to make modifications to the second shift register. This shift register contains the actual dashboard data. This is the data that's going to be sent from the robot to the dashboard program running on our driver station. It's a shift register, so we know that it keeps its value from loop to loop to loop. And what happens inside this case structure is different values are inserted into the shift register. So for example, if we were to take a look at the default case of this case structure, nothing happens. The input value coming from the shift register terminal is wired directly to the output value. Whereas if we're in steps 0 to 15, then depending on the value of some enable bits, certain information is added back in to that cluster. So we see here in steps 0 through 15, information is pulled out from the top value using this unbundle function, modified, voltage is read, inserted into an array, and then rebundled into the cluster. This code may look a little bit daunting, but the good news is we don't have to change it. In fact, we probably shouldn't. But what is important to know is that we observe that these Boolean values are actually coming from this control here. It's called the dashboard enables control. And this is where we tell this VI which inputs and outputs we want to send back to the computer running at our driver station. So 0 through 15 are reserved for analogs. 20 and 30 are reserved for digital inputs and outputs, as well as PWM values. 40 is reserved for the states of the solenoid values. And all of the other counter values will go to the default state, which does nothing. So before we go any further and before we modify this VI at all, let's take another look at this dashboard enables. If we double click on the terminal to bring it up in the front panel, we see here that it is a cluster which contains a bunch of Boolean values. And here is where we can turn on or off whether we want this information to be sent back to the dashboard project. If we return just for a very quick second while we're on this topic to the robot main VI, we see that although it's an input wired to the front panel, by default there is no wire connected to the dashboard enables. What that means is, unless we wire something here, this will use the default value as defined by the VI itself. So if we're going to leave the architecture alone, what we need to do whenever we need to change these enables from their default values is to be sure that we save these default values. And the way to do that is you right-click on the edge of the control, Data Operations, make Current Values Default, and then Save. And if you do that, you'll ensure that these values will be remembered every time that the robot program runs. So now that we've talked about the default behavior of the dashboard, we don't need to do anything more unless you want to make changes and add custom data back to the dashboard application. And I think it's probably pretty likely that you will. If you want to debug the states of your state machines, you want to watch what's going on in your robot, if you have any other parameters that are being tracked that you want to be able to watch in the driver station. So let's return to the block diagram. Remember that dashboard data is being contained within our shift register here. And if we want to add custom information, we need to edit the data type of this dashboard data. So luckily, when we right-click on this indicator here, we see that it's a type def. So if we open up our type def, we see by default all the PWM, digital, analog, and solenoid values. If we want to add some custom information, we just need to bring it into this type def. So let's add a couple important internal values from our mechanical lifter that we built in the previous videos. So let's go back to robot main, then to our lifter sub-VI, take a look at the block diagram, and remember that what we're outputting from this shift register is being put into the lifter type def global. So all that information is being placed in the global specifically so that we can take a look at it back at our robot main in our debug dashboard. So if we want that same capability in our driver station dashboard, why not make some of that same data available inside our dashboard type def? So if we open up our debug dashboard, show the block diagram, remember that we're taking these values and displaying them here. So all we need to do is go to the front panel, copy these controls, return to our dashboard data type, and paste them in. So now, by adding these controls here, we've changed the data type of the dashboard data type. So we apply changes, save and close this type def, and go back to our build dashboard data. So we've done part of the task. We've added the extra data we want into the data type, but we haven't written it anywhere. So what we need to do is modify this code by adding a case where we're going to write that data into this shift register. So why don't we take a duplicate of our default case, which by default will take the first available undefined numeric value, which is 16. And in this case, we're going to say update the lifter data. So again, whatever we put in this code is only going to run when the counter value, when divided by 50, gives a remainder of 16. What we need to do in here is bundle by name, and modify this bundle by name so that it accesses the parameters we want to write to. So the only thing left to do is actually get those parameters. Well, one of the reasons we created that global variable, which can be read anywhere but only written to in the lifter sub-VI, is so that we can read them in this kind of application. So let's return to the lifter state machine sub-VI, take a copy of our global, and paste it in here. Change it to read, and unbundle by name. So we're going to extract just those parameters that we want to put into the dashboard VI. And then we just need to connect these guys up. A natural question would be, why didn't we put this entire global variable into our dashboard? Well, that's certainly a possibility. You could do that, but you want to minimize the amount of data you put into this dashboard control, because that data is going to be sent from the robot to the program running at our driver station as often as possible. So you want to minimize the quantity of data. If it's not really required, for example, the device references for all the switches and motors are really not of any value back in the dashboard application. However, the values of the sensors and maybe the internal state of the lifter certainly are. So now, once we save and close our dashboard data and our lifter sub-VI and everything else, we've essentially made the modifications we need to put custom information into the dashboard data. So now what we need to do is create the dashboard project. And we can do that from the File menu by choosing New and choosing the FRC Dashboard project from the selection box. If we do that, we can specify the project name, the project location, click Finish, and it will automatically create the project we need. It's important to note that you're creating two projects for this application. One is the robot project, and the dashboard project is separate. Remember that all of the code within the robot project executes underneath the CREO target, while all the code on the dashboard project runs underneath my computer. So let's open up the dashboard main VI, and what we see when we do that is a pre-created dashboard project which shows us the camera image, the values of analog inputs, values of PWM and digital outputs for both slot 4 and slot 6, solenoid output, battery level, and communication information, as well as some match information, error messages, and user data. I'm going to just recommend you make two modifications to this VI. First, right-click on the icon of the VI and choose VI Properties. You may have noticed that the VI is set to be a certain size. If you choose Window Size and adjust the minimum panel size to be something much smaller, say even 800 by 600, then that will allow you to resize this project to fit a laptop screen which may not have as high resolution as necessary to show this whole thing at once. The second modification I would recommend is again to access VI Properties by right-clicking on the icon, choose Window Appearance, and then customize this appearance. If you were to run it right now, you'd notice that the scroll bars are disabled. Again, if you have a small or a low-resolution laptop screen, you may want to enable the scroll bars so that it's possible to navigate within the VI even while it's running. So we'll activate both the vertical and the horizontal scroll bars. So now that we've made some modifications to the front panel, let's take a quick look at the block diagram. If we were to take a look at this code, we see that there's fundamentally two parallel loops. The top one is receiving camera images from the robot, and the bottom one is receiving status data from the driver station. This is the code that we're going to need to slightly modify to display the custom data we've put into the dashboard data. And if you scroll down a little bit further, you see that there's code which is loading a team logo from either a PNG or a JPEG file in the same location as this VI and displaying it on a picture indicator on the front panel. If we just double click on this, you'll see where that is. It's right here. If we return to the block diagram, we see underneath there's also some information being displayed about whether there's a problem with the IP address. So again, most of this code you should not change. We're only going to focus on what we need to modify in order to display this custom information. In the very center of the status receive is this function here. If we activate the context help, we see that this is called unflatten from string. And what it's doing is taking an array of bytes, which is being received from the robot, converting it to a string, and then converting that string into the data type specified by the wire in the top middle of this function. The output of this function matches exactly the input wired here. So what this function is doing is interpreting the byte stream of data being sent by the robot into the appropriate data type. Well, recall what we just did on the robot side. We made a modification to the dashboard data type, and we added a few parameters from our lifter state machine. It's critically important, because we changed that data type, that we must make the appropriate change in this VI. If we follow this wire back, we see that it's actually coming from this constant over on the left. This constant, we can verify by right-clicking on the edge, is not defined to be a typedef. So what we need to do is replace this constant with the typedef that we just created in our other project. So let's go back to the project window for the dashboard project. What we're going to do is add a file. What we're going to add is the dashboard data type from the robot project we just modified. We add that, and if we click on the Files directory, expand the tree, we'll see that this is one instance where we expect to see files existing in two different directories within our LabVIEW data. So take a look at what we've got here. Here's our dashboard project, which contains all of the files which were automatically created. And here, from our robot project directory, is our dashboard data type. And notice how it also has included a reference to the lifter state enum. Recall back that dashboard data type, we added the lifter state. And because that lifter state itself is a typedef, it has automatically linked that up and listed it in our files directory here. So everything here is as it should be. Now all we need to do is drag this dashboard data type onto our block diagram. Once we do that, and we can right-click on the edge to confirm yes, it's a typedef. And if we open that typedef, we see all of that information which we just added is there. And the nice thing is that it's now linked to the same file as the robot data type. So if we make a modification to this data type in either project, it will be reflected next time we load the opposite project. We're going to delete this constant and connect this up. Now let's take a closer look at what's happening on the other side of this unflattened from string. This is where the dashboard data is decoded, unbundled, and displayed in indicators. We return to the front panel for a moment and say, for example, we look at these PWM indicators. If we double click, we see that that cluster is here. So we don't need to change any of this information. We just need to additionally extract and display the variables we added. So take a look at this unbundle function. Look as we hover over all of these other parameters that these unbundled terminals are giving us exactly those indicators that we added. So what we can do is right-click and create an indicator for each of them. You may want to do a control drag to make a bunch more space in this part of the code so that you can cleanly add all these indicators. Just repeat this process. Right-click, create indicator, right-click, create indicator, and right-click, create indicator. Clean up our wires a little bit. Maybe even align our terminals and distribute them. There. So now we can double-click on any one of these terminals, jump to the front panel, and rearrange these indicators. Maybe we don't need the error messages to be quite so large, so let's resize that and move our 3 indicators to a more convenient location. Maybe even rearrange their labels a little bit. Then again, we can align, distribute, and now we've modified our dashboard so that we can see some custom information. So now let's return to our robot project. Go to robot main and run the VI. And once that VI is running, we can run the dashboard program and we'll see live updates of the values of the program. Right now we're seeing some error messages and a lack of images because I've got no camera connected at the moment. But what we do see is that the third PWM output is showing a negative value and our lifter state is showing moving down. So this is actually a verification that what we just set up is actually working, because our lifter mechanism, remember, is attached to PWM output 3. And if it's in the moving down, that's what we would expect our motor speed to be. I'm going to just scroll over a bit so that we can keep that information on the screen. And let's return to the robot main VI and drill down into our lifter sub VI. Remember that we've got the ability to simulate with these front panel inputs the values on this state machine. So to activate that, I'm going to just double click on my global variables to go to the simulate mode, turn it on, minimize this, and now we should be able to watch the output values of the FRC dashboard when we simulate the values in our lifter state machine. So if it's moving down, it's waiting for the lower limit switch. So when we push that, we see that it's gone to the wait for ball, and we see that the lower limit switch value has indicated. If we hit our ball sensor, we see that it goes through a delay, and then it moves up. And if we turn off these sensors, simulating real life, we'll see that the front panel on the FRC dashboard is also updating. And when we switch to the upper limit, it switches to the moving down state, and the process can repeat. So it's interesting to note that there is a slight lag, even in this situation. The lag is caused by a couple different things. Well, there is a communication lag between the robot and the main program. And also there's a tremendous overhead being created by the fact that we're running this lifter state machine, which is technically running on the robot, in our development computer. So what you will find is if you never open any of these VIs and you do not do any simulation and you leave the programs running on the robot exclusively, your overhead of communication and the responsivity of your dashboard will be greatly increased. So in summary, in this video, we talked about how to modify the robot project to put whatever information you need into the dashboard data type. Recall that in order to do that, you needed to modify the data type def, as well as make changes to the actual dashboard data sub-VI, which is writing that information in. And then we learned how to create the dashboard project and make the necessary modifications there. First, to refer to the proper data type so that it takes the same type def that's being used in the robot project. And secondly, how to extract all the information that you have added into that data type and modify the code so that it displays it in indicators. Thank you very much for watching. This has been Ben Zimmer from lvmastery.com. Bye for now.